Double integrals in polar coordinates. Let's briefly review the polar coordinate system. In the rectangular coordinate system, we can locate a point by measuring where it lines up on the x-axis and where it lines up on the y-axis. We can also locate a point by measuring the angle formed with the positive x-axis, also known as the polar axis, and the line segment drawn from the origin or the pole to that point. Now, when we take that distance r with that angle theta, we get a point in polar coordinates. Keep in mind that points in polar coordinates are not unique, because once I know the angle associated here, we can add revolutions to that angle and end up at the same point. There are a few basic formulas that you should know that relate x, y, r, and theta, and they are given here. Polar coordinates are often very convenient for describing certain regions in the xy plane. For example, if I'm looking at the unit circle, the rectangular equation for the unit circle is x squared plus y squared is equal to 1. But the polar coordinate is very simple, or the polar equation is very simple for this circle. This is basically all the points in the polar coordinate system that are 1 unit or less distance from the origin. So we can describe this region by simply saying r is a number between 0 and 1, and theta goes from 0 to 2 pi, right? Because if we rotate all the way around, and if we are 1 unit or less from the center of this circle here, we basically get this disk. So although it requires statements about two variables here, r and theta, these are very simple statements, whereas x squared plus y squared equals 1 is a much more complicated statement. Now consider the half circle here with another circle cut out of it. So this circle here has a radius of 1 unit, and this circle has a radius of 2 units. And I want all the points in between those two circles, but only in the upper plane. To describe this using a rectangular equation, we would have to make a statement about x squared plus y squared equals 4, x squared plus y squared equals 1, and the fact that we want all the points in between there. And so we would have to say something like x squared plus y squared is all the points in between 4 and 1, but also y has to be greater than or equal to 0 because we are not taking any points down here. This is rather complicated. But using polar coordinates, we can simply say r is a number in between 1 and 2, right? Because every point in here is between 1 unit and 2 units away from the origin. And theta simply rotates from 0 to pi. So again, it's very easy to describe this region using polar coordinates. And so in terms of integration, we like to use polar coordinates when the region that we are integrating on is easy to describe by using those coordinates. So now let's briefly discuss the concept behind finding volumes under a function using polar coordinates. So we're going to have a function z equals f of xy, and let's suppose that the domain we are integrating on is some sort of a polar rectangle. That is, it is a simple polar region where r is between a and b, and theta goes in between alpha and beta. So to find an area on such a region, we partition the region. So we partition the thetas, and we partition the r's. And we get a bunch of little boxes. They're not quite boxes, they're a little bit curved. But if you pick one of those boxes, it is approximately a rectangle. And so to find the area of this box, we just need to find the length and width of that box. So if I come over here to look at what that would look like up close, we can see that the measurement here is dr, right? Because there's not much difference between the distance from here to here and the distance from here all the way up to here. Both of those are a radius of some type, but there is a little bit of a difference between the two. So we call that distance dr. This distance here is an arc length. And to find an arc length, we have a formula for that. The arc length is equal to r times theta. But the angle for this little slice right here isn't theta, it's actually d theta, right? It's one of those small partitions. So the arc length here is going to be s is equal to r times d theta. And so dA, the area of this little slightly rectangular region there, is going to be the length times the width. And that's going to be r d theta multiplied by dr. Or we can write that as r dr d theta. And so the volume over such a region is simply going to be the double integral over that region of the function f of xy dA. So notice the notation here is exactly identical to what we used to do. But now dA is r dr d theta. And because we're using polar coordinates, we know that x is equal to r cosine of theta and y is equal to r sine of theta. So if we plug these quantities in for x and y, we end up getting double integral f of r cosine theta, r sine theta, times r dr d theta. R is in between a and b, and theta is in between alpha and beta. Now, when you're first doing these, it can seem a little bit complicated, but with a little bit of practice, it turns out to be pretty straightforward. So let's take a look at this example. We want to evaluate the double integral of the function 3x plus 4y squared, dA, where r is the region in the upper half plane bounded by the circles x squared plus y squared equals 1 and x squared plus y squared equals 4. So this is the region we looked at just a few minutes ago here. All right. So let's think about what are the bounds of this region. Well, again, we know r, the radius, is between 1 and 2, and theta is between 0 and pi because we are only taking the upper half plane, right? In other words, we're not taking the circle down here. So to set this up, all I need to do is take the double integral of f of r cosine theta, r sine of theta, times r times dr times d theta. R is going to be in between a and b, and theta is in between alpha and beta. So let's go ahead and look at each part of this. F of r cosine theta, r sine theta means that we are going to replace x with r cosine theta and replace y with r sine of theta. And so this becomes 3 times r cosine theta plus 4 times r sine of theta squared. And if we simplify this, this is 3r cosine theta plus 4r squared sine squared of theta. And then we know that a and b are 1 and 2, and alpha and beta are 0 and pi, respectively. And I think we are now ready to integrate. Let's just plug everything in. So when we do that, we're going to get the integral from 0 to pi of the integral from 1 to 2. f is now this function, so 3r cosine theta plus 4r squared sine squared of theta, and that gets multiplied by r dr d theta. So now, of course, we'll go ahead and multiply r to both of these. And so we get the following. Now we are going to take the integral first with respect to r, which means we are only integrating the variable r. Everything else can be considered to be a constant. So the integral from 0 to pi will be the next step. When we integrate 3r squared with respect to r, we get 3r cubed over 3, which is r cubed. Cosine of theta is just along for the ride there. Plus 4r cubed, when you integrate that, you get r to the fourth. And then sine squared of theta is, again, just along for the ride. We're going to evaluate that from r equals 1 to r equals 2. And when we're done doing that, we'll then integrate with respect to theta. So let's go ahead and plug in r equals 2 and r equals 1. So when we plug in r equals 2 here, we get 8, and here we get 16. So we have 8 cosine theta plus 16 sine squared of theta minus, and when we plug in r equals 1 here, we just get 1, of course. So cosine of theta plus sine squared of theta, and then d theta. All right, now let's go ahead and combine like terms. We have 8 cosine of theta minus 1 cosine theta, which is 7 cosine theta, and 16 sine squared theta minus 1 sine squared theta is 15 sine squared theta. Okay, and so now we just need to integrate with respect to theta. But remember, sine squared requires a half angle identity. So let's go ahead and bring that into the picture. All right, so there it is. And now we can integrate. There's one small step that I think we should do. This is 15 halves. Multiply that to 1 and multiply that to cosine 2 theta. And now we can go ahead with the integration. So we have 7 sine of theta plus 15 halves times theta minus 15 halves times, and the integral of cosine of 2 theta is 1/2 sine of 2 theta. And now we go from 0 to pi. Now, sine of pi is 0, sine of 2 pi is 0. And when you plug in 0 into all of these, you also get 0. So the only thing we really get here is plugging pi into here. And so that is giving us 15 pi over 2. In the next problem, we wish to evaluate the double integral of the function x squared plus y squared dy dx over this semicircle. And you'll notice right now it's actually set up to be done the usual way. So this is just straightforward, integration with respect to y first. Y is going to vary between 0 and the function square root of 1 minus x squared. And then x goes from -1 over to +1. Now we could certainly do it this way, but it's a little bit easier if we use polar coordinates. So let's first observe that r is a number between 1 and 0, and theta is an angle between 0 and pi. That perfectly describes this region. And then f of r cosine theta, r sine theta, is simply r cosine of theta quantity squared plus r sine of theta quantity squared. And this is r squared cosine squared plus r squared sine squared. And factoring out the r squared, we're left with cosine squared plus sine squared. But cosine squared plus sine squared is equal to 1. And so f of r cosine theta, r sine theta is just r squared. And so this integral becomes the integral from 0 to pi, then 0 to 1. The function is r squared, and then we have to multiply that by r dr d theta. That's the formula. And look at how easy this integral is to perform. We have r cubed dr d theta. The integral of r cubed is r to the fourth divided by 4. And this goes from r equals 0 to r equals 1 d theta. Plugging in r equals 1, we get 1/4. Plugging in r equals 0, we get 0. And so we quite literally have the integral of 1/4 d theta from 0 to pi. This, of course, is 1/4 theta from 0 to pi, which is 1/4 times pi minus 0, or simply pi over 4. So it's not that we can't integrate this with respect to x and y, but polar coordinates makes the problem much easier. In our next example, we wish to find the volume of the solid bounded by the plane z equals 0, which is just the xy plane, and the paraboloid z equals 1 minus x squared minus y squared. So here's the graph of our function z equals 1 minus x squared minus y squared. What is the domain down below? It appears to be a circle, but we need to describe it precisely. So the domain in the xy plane is basically where z equals 0 intersects this surface. So if we let z equal 0, this equation here becomes 0 equals 1 minus x squared minus y squared, which is the same as x squared plus y squared is equal to 1, which of course is the unit circle. Now, if we are integrating on the unit circle in polar coordinates, we can simply say r is a number between 0 and 1, and theta is a number between 0 and 2 pi. So in polar coordinates, this becomes the integral from 0 to 2 pi, and then the integral from 0 to 1. Now we have to get our function in terms of r and theta. So f of r cosine theta, r sine theta, is going to be 1 minus r squared cosine squared minus r squared sine squared. And this can be simplified to 1 minus r squared times the quantity cosine squared plus sine squared, right? Because if I factor out the negative r squared, I have this left over. But this equals 1. And so this is simply 1 minus r squared. So our function is 1 minus r squared, and then don't forget you have to multiply by r dr d theta. And this integral is very easy to perform here. We have r minus r cubed dr d theta. And if we integrate that, we get r squared over 2 minus r to the fourth divided by 4 from r equals 0 to r equals 1. You don't have to write r equals, of course. You could just put from 0 to 1. Now let's plug in 1. We get 1/2 minus 1/4. And when you plug in 0, you get 0. And so this becomes the integral from 0 to 2 pi of 1/4 d theta. And this is 1/4 theta from 0 to 2 pi, which is 1/4 times 2 pi, or pi over 2. So again, we can do this problem without using polar coordinates, but it's much simpler to use polar coordinates. And you need to understand that what makes it simple is the fact that our domain in the beginning was this unit circle. So notice that when your domain is circular or something related to a circle, often polar coordinates will be a better way to do the problem. We can generalize this process. If f is a continuous function, on some polar region where theta is between two angles alpha and beta, but r is between two functions of theta, so not necessarily two numbers, but two functions of theta, we can still integrate using polar coordinates in exactly the same way. It's just that now r will be between two functions of theta instead of two numbers. So let's use a double integral to find the area enclosed by one loop of the four leaved rows. R equals the cosine of 2 theta. So let's remember that if you want to get the area of some domain D, so you have some domain D in R2, all you need to do is integrate over that domain D, and your function is 1 dA. So remember, this is if you find the volume of an object that has a height of 1 unit, it's the same as the area of the base. Well, that's what we're going to be using here. So the area here is going to be the double integral of our domain. So now we have to describe, well, what is our domain? But the function is just going to be 1, and then r dr d theta, right? Because our function in xy is just going to be 1. So our function in r cosine theta, r sine theta is still just going to be 1. So really it's just a matter of describing this domain here. So let's recognize that this domain, if we started at theta equals 0, we can take angles up to pi over 4, and that would give us this area. And we can see the symmetry. This area down here is equal to that area. So we could just find this area and double it. Or if you want, you could simply go from negative pi over 4 to positive pi over 4. But I like doubling. I like using symmetry whenever we can. So I'm going to integrate from 0 to pi over 4, multiply it by 2. And now what are the limits on r? Well, we have to recognize that r is the distance from here to the curve. And this is the curve r equals cosine of 2 theta. So r goes from 0 to cosine of 2 theta. Now let's just perform the integration. So we have 2 integral 0 to pi over 4. The integral of 1 times r with respect to r, of course, is r squared over 2. We're going to evaluate that from r equals 0 to r equals cosine of 2 theta. D theta. Now, if you want here, you can go ahead and just cancel these 2's. I think that's a good idea. Let's go ahead and do that. So what we have now is the integral from 0 to pi over 4. And then r squared, you're going to plug cosine of 2 theta in there. So that's cosine squared of 2 theta. D theta. Of course, when you plug in 0, you get 0. And now we have to do this integral, which means we need to use a half-angle identity. The half-angle identity for cosine squared of 2 theta is 1 plus cosine of 4 theta divided by 2, and you can factor that out as a 1/2. And now we simply need to integrate. So this is 1/2 times theta plus 1/4 sine of 4 theta, or 1/2 theta plus 1/8 sine of 4 theta. And now we go from 0 to pi over 4. Plugging in, we have 1/2 times pi over 4 plus, when you plug in pi over 4 here, you end up getting sine of pi, which is 0. Minus, and then when you plug in 0, you actually get 0. So the answer here in the end is pi over 8. In our final example, we wish to find the volume of the solid that lies under the paraboloid, so this is our function, above the xy plane, and inside of the cylinder x squared plus y squared equals 2x, which is this object here. Now, if you project that down into the xy plane, that is this circle. This circle can be described by recognizing that the equation for this circle in polar coordinates is r equals 2 cosine of theta. Now, you might remember that from polar coordinates or you might not. So let me show you how you can determine that. So we know that in polar coordinates, x is r cosine theta and y is r sine theta. So when we have x squared plus y squared is equal to 2x, remember also x squared plus y squared is r squared. So I can replace this with r squared, and then 2x becomes 2 times r cosine theta. And if we divide by r, we get r equals 2 cosine of theta. So that is the polar equation for this circle. So now when we integrate, we're going to have the double integral. One other fun fact about this is this circle actually gets traced out when theta is between 0 and pi. You don't have to go to 2 pi. You can try it out on your own. But it's going to be from 0 to pi. And then your r goes from 0 to 2 cosine theta. And then we have to have f of r cosine theta, r sine theta. So let's figure that out. Well, that's actually really simple, isn't it? Because z is equal to x squared plus y squared. But we know in polar coordinates, x squared plus y squared is r squared. So this is just z equals r squared. Now, if you don't see that, you can also do z equals r cosine theta squared plus r sine theta squared, which is r squared cosine squared plus r squared sine squared. And if you factor out the r squared, you end up getting cos squared plus sine squared, which is 1. And of course, this is equal to r squared. But it's much easier just to recognize x squared plus y squared is r squared. So the function is going to be r squared and then times r dr d theta. This, of course, is the integral of r cubed, which is the integral of, first integral is r to the 4th over 4, from 0 to 2 cosine of theta, d theta. So this becomes the integral from 0 to pi of 2 cosine of theta quantity to the 4th power divided by 4 d theta, right? Got to plug this into here. When you plug in 0, you get nothing. 2 to the 4th power is 16, divided by 4 is 4. And then we have cosine to the 4th power of theta. So now we need to use the half angle identity twice. So if we do that, we're going to have 4 integral. Cosine to the 4th of theta is cosine squared of theta quantity squared. Cosine squared is 1 plus cosine of 2 theta divided by 2. And then we have to square that. Squaring the 2 here gets 4, which cancels the 4 here. So we end up with the integral from 0 to pi of 1 plus cosine of 2 theta quantity squared. We need to multiply this out. And then we have to apply the half angle identity one more time. So this becomes the integral from 0 to pi, 1 plus 2 cosine 2 theta, plus 1/2 times 1 plus the cosine of 4 theta d theta. Now let's go ahead and combine like terms. You'll notice that we have 1 plus 1/2, which is 3 over 2, plus 2 cosine of 2 theta, plus 1/2 cosine of 4 theta. Integrating, we have 3/2 theta, plus 2 times 1/2 sine of 2 theta, plus 1/2 times 1/4 sine of 4 theta, from 0 to pi. This is 3 pi over 2. When we plug pi in here, we get 0. When we plug pi in here, we get 0. And when you plug 0 in all of these, you get 0. So the answer is 3 pi over 2. And that concludes this video lesson.